the early 1960s, a young aerospace engineer named Gary Flandreau sat at his desk at the Jet Propulsion Laboratory in Pasadena, California, working through a problem that would quietly change the future of space exploration. His task seemed modest enough. He had been asked to study whether it might be possible to send a spacecraft to the outer planets, to Jupiter, perhaps Saturn, using the gravitational pull of one world to accelerate toward the next. It was a technique that existed mostly in theory at the time, a mathematical concept known as gravity assist, in which a spacecraft could swing past a massive planet and borrow a fraction of its orbital energy, gaining speed without burning a single drop of fuel. What Flandreau discovered was something far more extraordinary than a route to one or two planets. As he charted the orbital positions of Jupiter, Saturn, Uranus, and Neptune across the coming decades, he realized that in the late 1970s, all four giant planets would be arranged along the same rough arc of the solar system. It was a geometric alignment that occurs only once every approximately 175 years. A spacecraft launched at the right moment could visit not just one or two of these worlds, but all four, swinging from Jupiter to Saturn, from Saturn to Uranus, and from Uranus to Neptune, carried forward by the gravity of each planet in turn. It was an almost impossibly rare opportunity, and the window would not remain open for long. If humanity missed it, no one alive at the time would ever see it return. The idea became known as the Grand Tour, and although funding limitations and political realities would eventually force NASA to scale back its original vision, the essential dream survived. By the early 1970s, the agency approved a more focused mission: 2 identical spacecraft, each designed to visit at least Jupiter and Saturn, with the possibility, if everything went well, that one of them might continue onward to the ice giants beyond. They were given a simple name: Voyager. The 2 spacecraft were built at the Jet Propulsion Laboratory, assembled by hand in clean rooms by engineers who understood that every component, every wire, every instrument had to function reliably across distances no machine had ever traveled. There would be no repair missions, no second chances. Once each Voyager left Earth, it would be entirely on its own, carrying out its observations with whatever it had on board at the moment of launch. Each spacecraft weighed roughly 825 kilograms. At the center was a 10-sided bus housing computers, propulsion systems, and power electronics. Extending outward were booms carrying magnetometers, plasma instruments, and the spacecraft's nuclear power source: 3 radioisotope thermoelectric generators filled with plutonium-238, designed to convert the heat of radioactive decay into electricity. Unlike solar panels, which would become useless in the dim light beyond Mars, these generators would continue providing power for decades. Mounted on a steerable platform were cameras, spectrometers, and infrared sensors. Together, these instruments would allow the Voyagers to photograph planetary atmospheres in fine detail, analyze the composition of gases and clouds, measure magnetic fields, detect charged particles, and listen for radio emissions from the giant planets and their moons. No interplanetary spacecraft had ever carried such a comprehensive suite of scientific instruments. But perhaps the most quietly remarkable object aboard each Voyager was something that had nothing to do with science at all. Bolted to the side of each spacecraft was a golden phonograph record, a 12-inch disc plated in gold, enclosed in an aluminum cover, and engraved with symbolic instructions for how to play it. The record contained 115 images of life on Earth, greetings spoken in 55 languages, a collection of natural sounds: wind, rain, birdsong, whale calls, and 90 minutes of music drawn from cultures around the world. It had been assembled by a small team led by the astronomer Carl Sagan, and it was intended not as a scientific instrument, but as a message, a quiet introduction from one civilization to the vast silence of interstellar space. No one expected the record to be found. The chances of another civilization encountering either Voyager in the emptiness between the stars were acknowledged to be extraordinarily small. But the team believed the gesture mattered. It was, in Sagan's view, something hopeful, a statement that humanity had once existed, that it had reached outward, and that it had thought to say hello. On the 20th of August 1977, Voyager 2 launched from Cape Canaveral aboard a Titan IIE Centaur rocket. 16 days later, on the 5th of September, Voyager 1 followed. Despite launching second, Voyager 1 was placed on a faster trajectory, one that would carry it to Jupiter and Saturn more quickly, though along a path that would not allow it to continue to Uranus or Neptune. Voyager 2, traveling more slowly, was aimed along the Grand Tour trajectory, the route that, if everything worked, would take it past all 4 giant planets over the course of 12 years. As both spacecraft climbed away from Earth and crossed the orbit of Mars, the distances began to grow in ways that reshaped every aspect of the mission. Comets sent from Earth traveled at the speed of light, but even light needed minutes, then tens of minutes, then hours to cross the growing void. Every instruction, every course correction, every software update had to be transmitted across a silence that expanded with every passing day. The Voyagers were not simply flying toward Jupiter. They were flying into a kind of loneliness no human object had ever known. And the universe ahead of them was waiting. Jupiter had been observed from Earth for centuries, through even modest telescopes. Its banded atmosphere was visible. Pale zones and darker belts wrapped around an enormous sphere of hydrogen and helium, crowned by the Great Red Spot, a storm system so large that the entire Earth could fit inside it with room to spare. Astronomers had measured its size, estimated its mass, catalogued 4 large moons first seen by Galileo in 1610, and detected powerful radio emissions, suggesting the planet was surrounded by an intense magnetic field. But everything known about Jupiter before 1979 had been assembled from a distance of at least 600 million kilometers. The Pioneer missions, Pioneer 10 in 1973 and Pioneer 11 in 1974, had returned the first close-range images, confirming the planet's immense radiation belts and offering tantalizing glimpses of atmospheric detail. Yet those were brief encounters, fast flybys with limited instruments. The Voyagers carried far more capable eyes. Voyager 1 began observing Jupiter in January of 1979, still tens of millions of kilometers away. Even at that range, the spacecraft's cameras revealed atmospheric features sharper than anything ground-based telescopes had achieved. Swirling oval storms appeared in unexpected numbers. Turbulent eddies churned along the boundaries between belts and zones. The Great Red Spot, long assumed to be a relatively stable structure, was surrounded by complex wind patterns that suggested a far more dynamic atmosphere than anyone had predicted. As Voyager 1 closed the distance through February and into March, the images became extraordinary. Cloud formations revealed themselves in layers ammonia ice crystals at the highest altitudes, ammonium hydrosulfide clouds below, and deeper water clouds inferred from the behavior of rising convective plumes. Wind speeds measured by tracking individual cloud features exceeded 500 kilometers per hour in some regions. The atmosphere was not merely decorative, it was a vast, turbulent engine driven by internal heat. Jupiter radiates nearly twice as much energy as it receives from the Sun, and the Voyagers were seeing the visible surface of that engine in unprecedented detail. On the 5th of March, 1979, Voyager 1 made its closest approach to Jupiter, passing within 349,000 kilometers of the cloud tops. During the hours surrounding closest approach, the spacecraft turned its instruments toward the planet's moons. And what it found there would fundamentally alter the course of planetary science. The first surprise came from Io, the innermost of the 4 large Galilean moons. Io had been expected to be a quiet, cratered body, a dead world, shaped by ancient impacts, similar in appearance to Earth's own moon. Instead, the images revealed a world unlike anything ever seen. The surface was covered in vivid reds, oranges, yellows, and whites. There were no visible impact craters at all. And, rising above the limb of the moon, silhouetted against the blackness of space, a navigation engineer named Linda Morabito noticed a faint, umbrella-shaped plume extending nearly 300 kilometers above the surface. It was a volcanic eruption, active, ongoing, and enormous. Further analysis revealed not 1 but 9 active volcanic eruptions occurring simultaneously across Io's surface. The moon was the most volcanically active body in the entire solar system. Its surface was being continuously resurfaced by sulfur and sulfur dioxide eruptions, which explained the complete absence of impact craters. Any craters that formed were simply buried beneath fresh volcanic material within relatively short geological timescales. The source of this extraordinary activity was tidal heating. Io orbits Jupiter at a distance of only 422,000 kilometers, locked in a gravitational relationship with the massive planet and its neighboring moons, Europa and Ganymede. This orbital resonance forces slight eccentricities in Io's orbit, causing Jupiter's gravitational pull to flex and squeeze the moon's interior with every revolution. The friction generated by this constant flexing produces enormous amounts of heat, enough to maintain a partially molten interior and drive volcanic activity on a scale unmatched anywhere else in the known solar system. No one had predicted it. The discovery of active volcanism on Io was one of the most significant findings of the entire Voyager program, and it arrived within the first planetary encounter. Europa, the next moon outward, presented an entirely different mystery. Its surface was remarkably smooth, among the smoothest in the solar system, covered in a shell of water, ice crisscrossed by long, dark linear features that stretched for hundreds and sometimes thousands of kilometers. There were almost no impact craters, suggesting the surface was geologically young. The linear features appeared to be fractures in the ice, and their patterns hinted that the ice shell might be moving, shifting, perhaps floating on something beneath. The implication was profound. If Europa's ice was relatively thin and actively resurfacing, something beneath it must be providing heat and mobility. The most compelling explanation was a subsurface ocean, a global layer of liquid water maintained by tidal heating, similar to that driving Io's volcanism, though less intense. Voyager's instruments could not confirm the ocean directly, but the visual evidence planted a question that would guide planetary science for decades to come. Ganymede, the largest moon in the solar system, larger even than the planet Mercury, revealed a surface divided into 2 distinct terrain types: dark, ancient, heavily cratered regions and lighter, younger regions marked by grooves and ridges suggesting tectonic activity in the distant past. Callisto, the outermost Galilean moon, appeared as one of the most heavily cratered objects ever observed, its ancient surface largely unchanged for billions of years, offering a frozen record of the early bombardment history of the outer solar system. 4 moons, each utterly different from the others, each orbiting the same planet. Jupiter was not merely a giant world with satellites. It was the center of a miniature planetary system, diverse and complex in ways that no one had fully anticipated before Voyager arrived. Beyond the moons, Voyager 1 made another unexpected discovery. As the spacecraft passed through Jupiter's equatorial plane, its cameras detected a faint, thin ring encircling the planet. Jupiter's ring had never been observed from Earth. It was far too tenuous, composed of fine dust particles, rather than the large ice chunks that make Saturn's rings so prominent. but it was real, and its existence added Jupiter to the list of ringed planets. A list that, by the end of the Voyager program, would include all 4 giant worlds. 4 months after Voyager 1's encounter, Voyager 2 arrived at Jupiter in July of 1979. Its trajectory was different, optimized for the grand tour path that would carry it onward to Saturn, Uranus, and Neptune, but it carried the same instruments. And the 4-month gap between the 2 encounters offered something invaluable: the ability to observe change. Atmospheric features that had been prominent during Voyager 1's flyby had shifted, evolved, or disappeared entirely. Storms had formed. The great red spots surrounding cloud patterns had rearranged. Jupiter's atmosphere was not simply dynamic. It was restless on timescales of weeks and months, far more variable than the centuries of telescopic observation had suggested. Voyager 2 also returned improved images of the moons, capturing different hemispheres and confirming many of Voyager 1's discoveries, while adding new detail. Europa's fractured ice surface was examined more closely, and the complexity of its crack patterns deepened the suspicion that the ice was geologically active. Io continued to erupt, though some of the plumes had changed in size and location, confirming that the moon's volcanic activity was not static, but continuously evolving. Together, the 2 Jupiter encounters transformed the planet from a distant striped giant into a world of staggering complexity, a world with active moons, faint rings, violent radiation belts, and an atmosphere that behaved more like a living system than a static backdrop. The data returned by both spacecraft would fuel scientific research for years, filling journals with papers on atmospheric dynamics, magnetospheric physics, satellite geology, and the mechanics of tidal heating. But the Voyagers did not linger. Jupiter's gravity had already done its work, bending each spacecraft's trajectory and accelerating it toward the next destination. Saturn waited beyond, fainter and farther, surrounded by the most spectacular ring system in the solar system. The Grand Tour continued. Saturn had been the most distant planet known to ancient astronomers, a slow-moving point of golden light that took nearly 30 years to complete a single orbit around the Sun. When Galileo first turned his telescope toward it in 1610, he saw something peculiar. The planet appeared to have 2 companion objects, one on either side, as though it were flanked by ears or handles. His telescope was not powerful enough to resolve what he was seeing. It was not until 1655 that the Dutch astronomer Christian Huygens, using a better instrument, correctly identified the structures as a flat ring encircling the planet, tilted at an angle to our line of sight. In the centuries that followed, astronomers gradually resolved the ring into multiple concentric bands, identified gaps within the system, discovered a growing family of moons, and measured the planet's remarkably low density. So low that Saturn would float if placed in a body of water large enough to hold it. But even by the late 1970s, the rings remained deeply mysterious. Their composition was understood to be primarily water ice, but their structure, their dynamics, the forces that maintained their sharp edges, and intricate internal patterns. These were questions that could only be answered by a spacecraft flying close enough to see the details. Voyager 1 arrived at Saturn in November of 1980, nearly a year and a half after leaving Jupiter behind. As the spacecraft approached, the rings came into view with a clarity that no telescope had ever achieved. What had appeared from Earth as a handful of broad, smooth bands revealed itself to be an astonishingly complex system of thousands of individual ringlets, each one a narrow strand of orbiting ice particles. The rings were not simple structures. They were intricate, finely layered, and governed by gravitational interactions so subtle that many of their features defied immediate explanation. The Cassini division, the wide dark gap between the bright A and B, rings visible from Earth, turned out not to be empty at all. It contained faint ringlets of its own, dimmer and sparser than the main rings, but clearly present. The B ring, the broadest and brightest of the major rings, displayed strange radial features that the imaging team initially struggled to explain. Dark spoke like markings that rotated with the ring, yet did not follow the expected orbital mechanics of individual particles. These spokes appeared to be composed of fine dust levitated above the planes by electrostatic forces interacting with Saturn's magnetic field. They were transient, forming and dissipating over hours, and nothing like them had ever been observed or predicted. The thinness of the rings was equally remarkable, despite spanning over 270,000 kilometers. From inner edge to outer edge, the main rings were estimated to be no more than about 10 meters thick, in most places a ratio of width to thickness so extreme that if the rings were scaled down to the diameter of a football field, they would be thinner than a sheet of paper. This extraordinary flatness was maintained by the self-correcting dynamics of orbital mechanics. Any particle drifting above or below the ring plane would experience gentle gravitational pulls drawing it back, keeping the system confined to an impossibly thin disk beyond the rings. Voyager 1 turned its attention to Saturn's largest moon, Titan. Titan had long fascinated scientists because it was the only moon in the solar system known to possess a thick atmosphere. Ground-based observations had detected methane in its atmosphere, and there was speculation that the surface might harbor lakes or even seas of liquid hydrocarbons. But no one knew what Titan's surface looked like. Its atmosphere was opaque, a dense, orange haze that completely obscured whatever lay beneath. Voyager 1's encounter with Titan was given high priority. The spacecraft was directed to pass within approximately 6,400 kilometers of the moon's surface, closer than any other flyby target in the Saturn system. Scientists hoped the cameras might penetrate the haze at certain wavelengths, or at least resolve surface features through thinner regions of the atmosphere. But as the images arrived, the result was both scientifically valuable and visually frustrating. Titan appeared as a smooth, featureless orange sphere. The haze was too thick. No surface detail was visible at any wavelength. Voyager's cameras could detect. What the spacecraft did reveal, however, was extraordinary in its own right. The atmosphere was far denser than expected surface. Pressure was measured at approximately 1.5 times Earth's sea level pressure, making Titan the only body in the solar system other than Earth with a substantial nitrogen-dominated atmosphere. Temperature measurements indicated the surface was bitterly cold, around -179 degrees Celsius, a temperature at which methane could exist as liquid, solid, or gas, depending on local conditions. The atmospheric chemistry was rich and complex, with ultraviolet radiation from the distant sun, driving reactions between nitrogen and methane to produce a variety of organic compounds, the same types of molecules considered important precursors to biology on early Earth. Titan was not merely a moon with an atmosphere. It was a world with weather, chemistry, a surface environment that, despite the extreme cold, bore unsettling parallels to a young Earth. The decision to prioritize the Titan flyby came at a cost. However, the trajectory required for the close Titan encounter bent Voyager 1's path out of the ecliptic plane, the flat disk in which the planets orbit, making it impossible for the spacecraft to continue onward to Uranus or Neptune. Voyager 1's planetary mission effectively ended at Saturn. Its future would be a long, quiet journey outward, away from the planets entirely, toward the edge of the solar system, and eventually into interstellar space. The continuation of the grand tour now depended entirely on Voyager 2. Voyager 2 arrived at Saturn in August of 1981, 9 months after its twin. Its trajectory had been carefully designed to preserve the option of continuing to Uranus and Neptune, which meant its Saturn encounter was different in character, less focused on Titan, more focused on the rings and the smaller icy moons that populated the system. The spacecraft confirmed and expanded upon Voyager 1's ring discoveries. Additional fine structure was resolved. New small moons were found embedded within or near the rings, their gravitational influence helping to sculpt the sharp edges of certain gaps. 2 tiny moons, later named Prometheus and Pandora, were discovered, flanking the narrow F ring, their gravitational tugging keeping the ring confined in a braided, kinked structure that seemed to defy simple orbital dynamics. These shepherd moons, as they came to be called, provided an elegant explanation for how narrow rings could persist without spreading out. Over time, their gravity acted as invisible walls, nudging stray particles back into line. Voyager 2 also examined several of Saturn's icy moons more closely. Enceladus, a small moon only about 500 kilometers in diameter, displayed a surface that was partially ancient and cratered but partially young and remarkably smooth, with regions that appeared to have been resurfaced by some geological process. The smoothest areas showed few, if any, craters, suggesting they were perhaps only a few 100 million years old, extraordinarily young by solar system standards. Something inside this tiny moon had been active in the relatively recent past. Though Voyager's instruments could not determine what, the answer would not come for another 2 decades, when the Cassini mission would discover active water geysers erupting from Enceladus's south pole, but the seeds of that discovery were planted here. In the puzzling images returned by Voyager 2, Mimas, another of Saturn's moons, presented one of the most visually striking images of the entire mission. Its surface was dominated by an enormous impact crater named Herschel, roughly 130 kilometers across, nearly 1/3 the diameter of the moon itself. The impact that created Herschel must have come close to shattering Mimas entirely. The crater gave the small moon an appearance that many observers compared to a fictional space station, though the science behind it was a vivid reminder of the violent collisions that shaped the early solar system. Iapetus, orbiting much farther from Saturn, displayed one of the oldest mysteries in planetary astronomy, a dramatic 2-tone surface, with one hemisphere as dark as coal and the other as bright as fresh snow. Voyager 2's images confirmed the stark contrast, but could not fully explain its origin. Theories ranged from swept-up dark material from a distant outer ring to thermal migration of ice caused by differences in surface heating. Like so many Voyager discoveries, the observation raised more questions than it answered, leaving a trail of scientific curiosity that would occupy researchers for decades. As Voyager 2 completed its Saturn encounter, mission controllers at the Jet Propulsion Laboratory faced a critical decision. The spacecraft was functioning well, its instruments healthy, its power supply still adequate. The trajectory toward Uranus was achievable, but Uranus was nearly 3 billion kilometers from the Sun, a world so distant that sunlight there was roughly 400 times dimmer than on Earth. Communication signals would take over 2 hours to travel each way. No spacecraft had ever attempted such a distant encounter, and the engineering challenges were formidable. The decision was made to continue. Voyager 2 was aimed toward Uranus, and the Grand Tour reduced, reshaped, but still alive, pressed onward into the cold and the dark. Behind it, Saturn and its rings shrank slowly into the distance, becoming once again a small golden point of light, beautiful and silent, exactly as the ancient astronomers had always seen it. The journey from Saturn to Uranus took 4.5 years. During that long crossing, Voyager 2 traveled in near silence through a region of the solar system that no spacecraft had ever visited. The Sun, already small at Saturn, continued to shrink. Temperatures outside the spacecraft dropped further. The signal strength between Voyager 2 and Earth weakened with every passing month, the radio whisper growing fainter as the distance stretched beyond 2 billion kilometers, then past 2.5 billion, then toward 3. For the engineers at the Jet Propulsion Laboratory, those 4 years were not idle. They understood that the Uranus encounter would be unlike anything previously attempted. The light levels at Uranus were so low that the spacecraft's cameras would need much longer exposure times to capture usable images, but Voyager 2 would be moving rapidly during its flyby, and long exposures on a moving platform produced blurred photographs. To solve this, the engineering team developed a technique in which the entire spacecraft would rotate slowly during each exposure, precisely counteracting its own forward momentum relative to the target. This compensating rotation had to be calculated for every individual photograph, programmed into the spacecraft's aging computers, and uploaded across a signal delay that now exceeded 2.5 hours in each direction. If the rotation rate was even slightly wrong, the image would be smeared and unrecoverable. The computers aboard Voyager 2 had a total memory capacity of roughly 68 kilobytes less than a modern thumbnail image file. Every byte of programming had to be carefully managed. The software was rewritten and updated multiple times during the cruise to Uranus, with new routines transmitted from Earth to replace older code that was no longer needed. In a very real sense, the spacecraft that arrived at Uranus in 1986 was a different machine from the one that had left Saturn reprogrammed, recalibrated, and adapted for conditions its original designers had only partially anticipated. On the ground, the Deep Space Network NASA's global array of large radio antennas was also upgraded. The antennas at Goldstone in California, Canberra in Australia, and at Madrid in Spain were linked with additional radio telescopes to create larger effective receiving areas, boosting the sensitivity needed to detect Voyager 2's fading signal. Even with these upgrades, the data transmission rate from Uranus would be significantly slower than it had been at Jupiter or Saturn. Every image, every instrument reading, every byte of scientific data would trickle back to Earth at a pace that demanded extraordinary patience. Voyager 2 reached Uranus on the 24th of January, 1986, passing within approximately 81,500 kilometers of the planet's cloud tops. It remains, to this day, the only spacecraft ever to visit Uranus. What it found was a world profoundly different from Jupiter and Saturn. Uranus is classified as an ice giant rather than a gas giant, a distinction reflecting its internal composition. While Jupiter and Saturn are dominated by hydrogen and helium, Uranus contains a much higher proportion of heavier elements, particularly water, ammonia, and methane compressed into a hot, dense fluid mantle surrounding a small rocky core. The methane in its upper atmosphere absorbs red light and reflects blue-green wavelengths, giving the planet its distinctive pale cyan color, a color that in Voyager's images appeared remarkably uniform. Unlike Jupiter's dramatic bands and Saturn's subtle atmospheric patterns, Uranus presented an almost featureless face to the cameras. The atmosphere appeared calm, quiet, and eerily bland. This apparent stillness was partly misleading. Uranus possesses its extraordinary axial tilt of approximately 98 degrees, meaning it essentially rotates on its side relative to its orbital plane. The cause of this extreme tilt remains uncertain, but the prevailing hypothesis involves a massive collision with an Earth-sized protoplanet during the early history of the solar system, an impact violent enough to knock the entire planet sideways. As a consequence of this tilt, the poles of Uranus take turns pointing almost directly at the Sun over the course of its 84-year orbit. At the time of Voyager 2's encounter, the South Pole was aimed toward the Sun, meaning the entire southern hemisphere had been in continuous sunlight for decades, while the northern hemisphere remained in continuous darkness. Despite this unusual heating pattern, the atmosphere showed surprisingly little variation. Scientists had expected the extreme seasons to drive strong atmospheric circulation, but Uranus appeared to be the quietest of the four giant planets. Some faint cloud features were eventually detected in heavily processed images, and wind speeds were measured at several hundred kilometers per hour in certain bands, but the overall impression was one of deep, cold stillness. Internal heat emission was also puzzlingly low, unlike Jupiter and Saturn, which radiate significantly more energy than they receive from the Sun. Uranus appeared to radiate almost no excess heat at all. Something about the planet's interior seemed to trap or suppress the heat flow that drives visible atmospheric activity on other giant worlds. The mechanism remains poorly understood to this day. The magnetic field of Uranus provided another surprise. On Earth, Jupiter, and Saturn, the magnetic field is roughly aligned with the planet's rotation axis. The magnetic poles sit relatively close to the geographic poles. At Uranus, the magnetic field was tilted nearly 60 degrees away from the rotation axis and offset from the center of the planet by roughly 1/3 of its radius. The resulting magnetosphere was twisted and asymmetric, wobbling dramatically as the planet rotated. The geometry was so unusual that scientists initially questioned whether Uranus might be undergoing a magnetic field reversal, a process known to occur on Earth over geological timescales. But the later discovery of a similarly tilted field at Neptune suggested that offset, tilted magnetic fields might simply be a characteristic of ice giant interiors, where the field-generating dynamo operates in a thin shell of electrically conducting fluid, rather than deep within the core. Voyager 2 discovered 10 previously unknown moons during its flyby, bringing the total known at the time to 15. Most were small, dark, irregular bodies orbiting close to the planet. But the 5 larger moons, Miranda, Ariel, Umbriel, Titania, and Oberon, each offered their own surprises. Miranda, the smallest of the 5 major moons, at only about 470 kilometers in diameter, was perhaps the most astonishing. Its surface was a patchwork of wildly different terrain types, smooth plains adjacent to heavily cratered regions, enormous fault canyons cutting across the surface, and bizarre chevron-shaped features called coronae that looked like nothing else in the solar system. One cliff face, later named Verona Rupes, dropped approximately 20 kilometers from rim to base, making it one of the tallest known cliff faces in the solar system. The surface of Miranda looked as though the moon had been broken apart and reassembled incorrectly, and for a time, some scientists genuinely proposed that scenario, that Miranda had been shattered by a massive impact and gravitationally reaccumulated into a jumbled, disordered sphere. Later analysis suggested the features were more likely the result of internal geological processes, perhaps driven by tidal heating from an earlier orbital resonance. But the visual impact of Miranda's tortured landscape remains one of the most striking images in the Voyager archive. Ariel showed evidence of relatively recent geological activity, with smooth plains and extensive fault valleys suggesting internal resurfacing. Umbriel was darker and more heavily cratered, its ancient surface largely undisturbed. Titania and Oberon, the 2 largest moons, displayed moderately cratered surfaces with some evidence of past tectonic activity, long fault scarps and grabens, suggesting their interiors had once expanded, cracking the surface as they cooled. Voyager 2 also confirmed the existence of a ring system around Uranus, which had first been detected from Earth during a stellar occultation in 1977. The rings were narrow, dark, and composed of particles that reflected very little light, strikingly different from the bright icy rings of Saturn. The largest ring, called the Epsilon Ring, was only a few tens of kilometers wide and shepherded by 2 small moons, much like Saturn's F ring. The other rings were even narrower and fainter, barely visible even from Voyager's close range. Uranus was a world that resisted easy understanding. Its quiet atmosphere, extreme tilt, anomalous magnetic field, negligible internal heat, and battered collection of icy moons painted a portrait of a planet shaped by forces that remain only partially explained. It was neither as dramatic as Jupiter nor as visually spectacular as Saturn, but in many ways its mysteries ran deeper because there was so little activity on the surface to hint at what was happening within. Voyager 2 spent only a matter of hours in close proximity to Uranus. The geometry of the flyby provided a gravitational assist that bent the spacecraft's trajectory southward, out of the ecliptic plane, and aimed it toward the final target of the Grand Tour, a world even more distant, even dimmer, and even less understood. Neptune lay ahead, 4.5 billion kilometers from the Sun, and Voyager 2 would need another 3.5 years to reach it. The crossing from Uranus to Neptune was the loneliest passage of the entire mission. Voyager 2 traveled for 3.5 years through a region of space so remote that the Sun appeared as little more than an unusually bright star. At Neptune's distance of approximately 4.5 billion kilometers, sunlight was nearly 900 times dimmer than on Earth. A human standing on Neptune's cloud tops at noon would experience a light level roughly equivalent to twilight on Earth, enough to see by, but only barely. For Voyager 2's cameras, this meant that every engineering challenge encountered at Uranus was now amplified. Exposure times needed to be even longer. The compensating rotation maneuvers had to be even more precise. The data transmission rate from that distance was reduced to a trickle, and every image took longer to reach Earth than the one before. The engineering team at the Jet Propulsion Laboratory spent the entire cruise preparing. Software was again rewritten and uploaded. Compression algorithms were refined to extract maximum information from minimum data. The deep space network's receiving capabilities were pushed further, with radio telescopes in Australia and New Mexico linked to the main Canberra antenna to form an array sensitive enough to detect Voyager 2's whisper across 4.5 billion kilometers of empty space. On the 25th of August, 1989, 12 years, one week, and 3 days after leaving Earth, Voyager 2 arrived at Neptune. What awaited was nothing like Uranus, where Uranus had presented a calm, nearly featureless atmosphere. Neptune was alive with motion, even from a distance. The approaching spacecraft detected dark spots, bright cloud streaks, and banded structures suggesting powerful atmospheric circulation. As the images sharpened during the final approach, a massive storm system became visible in the southern hemisphere, a dark, oval anticyclone, roughly the size of Earth, immediately named the Great Dark Spot. Its resemblance to Jupiter's Great Red Spot was superficial but striking. Bright white clouds of methane ice crystals hovered along its southern edge, casting shadows on the deeper cloud deck below. The first time shadows had been observed within any planet's atmosphere from a spacecraft, providing a direct measurement of the altitude difference between cloud layers. The winds on Neptune proved to be the fastest measured on any planet in the solar system. In the equatorial region, atmospheric features were tracked moving westward against the direction of the planet's rotation at speeds exceeding 2,000 kilometers per hour. This was deeply puzzling. Neptune receives very little energy from the Sun compared to Jupiter or Saturn, yet its atmospheric dynamics were among the most violent ever observed. The energy driving these extreme winds had to come primarily from within the planet itself. Unlike Uranus, which radiates almost no excess internal heat, Neptune radiates approximately 2.5 times more energy than it receives from the Sun. The source of this internal heat remains a subject of active research, but its consequences were visible in every image. Voyager returned a distant, freezing world with an atmosphere more turbulent than planets, receiving many times more solar energy. Smaller storm systems were also observed. A feature named the Small Dark Spot appeared farther south, and a bright, fast-moving cloud, nicknamed Scooter, raced around the planet at a different latitude, overtaking the Great Dark Spot with each rotation. Neptune's atmosphere was layered, dynamic, and complex, with wind patterns that varied dramatically by latitude. Methane in the upper atmosphere gave the planet its deep blue color a richer, more vivid blue than the pale cyan of Uranus, suggesting differences in atmospheric composition or the vertical distribution of haze layers between the two ice giants. The magnetic field of Neptune echoed the strangeness found at Uranus. Like its neighbor, Neptune's magnetic field was dramatically tilted approximately 47 degrees from the rotation axis and offset from the planet's center by more than half its radius. The magnetosphere was twisted and irregular, confirming that the unusual magnetic geometries observed at Uranus were not unique anomalies, but likely characteristic of ice giant interiors. The field-generating dynamo in both planets appears to operate in a relatively thin shell of electrically conducting fluid, probably a mixture of water, ammonia, and methane compressed to extreme pressures, rather than in a deep metallic hydrogen core like those of Jupiter and Saturn. This fundamental structural difference between gas giants and ice giants was one of the key insights to emerge from Voyager 2's back-to-back encounters with the two outermost planets. But if Neptune's atmosphere and magnetosphere rewrote expectations, its largest moon delivered the encounter's most unforgettable moment. Triton orbits Neptune in a retrograde direction, opposite to the planet's rotation, at a steep inclination to Neptune's equatorial plane. This unusual orbit is strong evidence that Triton did not form alongside Neptune, but was instead captured from the Kuiper Belt, the vast reservoir of icy bodies that extends beyond Neptune's orbit. If this capture hypothesis is correct, Triton is the largest captured object in the solar system, a world roughly 2,700 kilometers in diameter that was once a free-roaming Kuiper Belt object before Neptune's gravity trapped it into orbit. The capture would not have been gentle. Triton's originally eccentric orbit would have been gradually circularized over millions of years by tidal interactions with Neptune, and the enormous tidal energy dissipated during this process would have heated Triton's interior, dramatically potentially maintaining a subsurface ocean for a significant portion of the Moon's history. Whether any such ocean persists today remains unknown, but the possibility has placed Triton on the growing list of solar system worlds where liquid water might exist beneath an icy surface. Voyager 2 passed within approximately 40,000 kilometers of Triton's surface, and the images it returned were stunning. The surface was extraordinarily varied: bright nitrogen ice plains, pinkish terrain, colored by organic compounds produced through ultraviolet radiation, interacting with nitrogen and methane, and a strange landscape in the southern hemisphere that the imaging team described as cantaloupe terrain, a pattern of roughly circular dimples and ridges that resembled the skin of a melon. The origin of this terrain remains debated, but it may result from a process called diaporism, in which less dense material rises through denser surface layers, creating dome-like structures that then collapse. The surface temperature was measured at approximately minus 235 degrees Celsius, making Triton the coldest surface ever measured on any visited body in the solar system. At that temperature, nitrogen freezes solid, forming a thin but visible polar cap of nitrogen ice that extended across much of the hemisphere facing Voyager's cameras. And then, against all expectation, Voyager 2 observed plumes. Dark streaks marked the surface of Triton's southern polar cap, each one extending downwind for distances of up to 150 kilometers. At the base of several streaks, narrow columns of dark material were seen rising vertically to an altitude of approximately 8 kilometers before being swept horizontally by thin winds in Triton's tenuous nitrogen atmosphere. These were active geysers, eruptions of nitrogen gas and dark dust particles, driven by a process believed to involve solar heating of subsurface nitrogen ice through a transparent frozen layer, building pressure until the gas erupted through the surface in narrow jets. The discovery of active geological processes on a world so cold and so distant from the Sun was one of the most remarkable findings of the entire Voyager mission. Triton was not dead, despite surface temperatures barely above absolute zero. Despite receiving only a fraction of 1% of the sunlight that reaches Earth, this captured moon was still geologically active, still reshaping its surface, still venting material into its thin atmosphere. Voyager 2 also discovered 6 previously unknown moons of Neptune during the encounter, all small and irregular, along with a system of faint rings. The rings were tenuous and clumpy, with denser regions called ring arcs that appeared to be confined by gravitational interactions with nearby small moons. The ring arcs had been tentatively detected from Earth through stellar occultations, but their nature had been debated. Some scientists had questioned whether complete rings existed at all. Voyager confirmed that the rings were real but sparse, and that the arcs represented denser concentrations of material within otherwise thin ring structures. As Voyager 2 swept past Neptune and Triton and continued southward, away from the ecliptic plane, the final planetary encounter of the Grand Tour came to a close. No spacecraft had visited all 4 giant planets before. No spacecraft has done so since. The alignment that made the journey possible had passed, and the next opportunity would not arrive for more than a century. In 12 years, Voyager 2 had transformed humanity's understanding of the outer solar system. It had revealed volcanic moons and frozen oceans, ring systems and tilted magnetic fields, turbulent atmospheres and geysers erupting on a world colder than almost anything else in the solar system. Each encounter had delivered surprises that no ground-based observation could have predicted, and each had raised new questions that would occupy planetary scientists for generations. Now, with no more planets ahead, Voyager 2 joined its twin in a different kind of mission, one with no flyby, no encounter, no destination, and no end. Both spacecraft were heading outward, toward the boundary of the solar system itself. On the 14th of February, 1996 months after Voyager 2's encounter with Neptune, something unusual happened aboard Voyager 1. The spacecraft, which had been traveling outward since its Saturn flyby a decade earlier, and was now approximately 6 billion kilometers from Earth, received a carefully prepared sequence of commands. The instructions directed the spacecraft to turn its camera platform back toward the inner solar system and take a series of photographs, not of any scientific target, but of the planets it had left behind long ago. The idea had come from Carl Sagan, who had been involved with the program since its earliest days. Sagan had proposed the photograph years earlier, arguing that the view of Earth from such an extraordinary distance would carry a perspective no other image could provide. The suggestion had initially met resistance within NASA. Some engineers argued that pointing the cameras back toward the Sun risked damaging the imaging system. Others questioned the scientific value. There was no new data to be gained from photographing a tiny dot of light billions of kilometers away. But Sagan persisted, and eventually the agency agreed. Voyager 1 captured a series of 60 frames, sweeping across the positions of 6 planets: Venus, Earth, Jupiter, Saturn, Uranus, and Neptune. Mercury was too close to the Sun to be distinguished. Mars was lost in scattered sunlight within the camera optics. But Earth was there, a tiny point of light, suspended in a beam of scattered sunlight, occupying less than a single pixel in the frame. The image was dim, grainy, and technically unremarkable. And it became one of the most famous photographs ever taken. Sagan later reflected publicly on what the image meant. He spoke about the smallness of Earth, the fragility of everything humanity had ever known, reduced to a fraction of a pixel in the vastness of space. He described wars fought over portions of that dot, empires risen and fallen on its surface, every human being who had ever lived, confined to its thin layer of atmosphere and rock. The photograph became known as the pale blue dot, and it resonated far beyond the scientific community. It was not a discovery. It was a perspective, a quiet, devastating reminder of scale that only a spacecraft 6 billion kilometers from home could provide. After the photograph was taken, Voyager 1's cameras were permanently shut down. There was nothing left to photograph. The spacecraft was heading away from all known worlds, and its power reserves, though still adequate for other instruments, could no longer justify the energy cost of maintaining an imaging system with no targets. The cameras that had revealed Io's volcanoes, Saturn's rings, and Uranus's fractured moon, Miranda, fell silent, and Voyager 1 became, from that point forward, a spacecraft that listened rather than looked. Both Voyagers had now entered a new phase of existence. Their planetary missions were complete. Their cameras were off. Their trajectories carried them steadily outward, away from the Sun, at speeds of roughly 17 kilometers per second for Voyager 1 and 15 kilometers per second for Voyager 2. They were still functional, still transmitting, still carrying instruments capable of measuring magnetic fields, charged particles, plasma waves, and cosmic rays, and they were heading toward a boundary that no human-made object had ever approached: the edge of the heliosphere. The heliosphere is the vast bubble of charged particles and magnetic field that the Sun inflates around itself. The solar wind, a continuous stream of protons, electrons, and heavier ions, flows outward from the Sun in all directions at speeds ranging from roughly 300 to 800 kilometers per second. This wind carries the Sun's magnetic field with it, creating a region of space dominated by solar influence. Within the heliosphere, the environment is shaped primarily by the Sun. Beyond it lies interstellar space, a region dominated by the magnetic fields, cosmic rays, and tenuous gas clouds of the broader Milky Way galaxy. The boundary between these two regions is not a sharp wall. It is a gradual transition zone with several distinct layers. The first is the termination shock, where the outward flowing solar wind abruptly slows from supersonic to subsonic speeds as it begins to encounter resistance from the interstellar medium. Beyond the termination shock lies the heliosheath, a turbulent region where the slowed solar wind piles up and mixes with increasing quantities of interstellar material. The outermost boundary is the heliopause, the point where the pressure of the solar wind is finally balanced by the pressure of the interstellar medium. Beyond the heliopause, the Sun's direct influence effectively ends. No one knew exactly where these boundaries were. Theoretical models predicted that the termination shock might lie somewhere between 75 and 100 astronomical units from the Sun. 1 astronomical unit being the average distance from Earth to the Sun, approximately 150 million kilometers. But the models carried significant uncertainty. The heliosphere is not perfectly spherical. It is shaped and compressed by the motion of the solar system through the surrounding interstellar medium, creating a blunt leading edge and a long, drawn-out tail. The exact distances to the boundaries depend on solar activity, the density of the local interstellar medium, and other variables that were poorly constrained. The Voyagers carried instruments specifically suited to detecting these transitions. Magnetometers could measure changes in magnetic field strength and direction. Plasma instruments could detect shifts in the composition and speed of charged particles. Cosmic ray detectors could register the increasing flux of high-energy particles from outside the solar system as the shielding effect of the heliosphere diminished. The spacecraft were, in a sense, perfectly equipped for this final mission. Even though no one had designed them for it, the instruments originally built to study Jupiter's magnetosphere and Saturn's charged particle environment turned out to be precisely the tools needed to explore the boundary between the Sun's domain and the galaxy beyond. In 1998, Voyager 1 surpassed Pioneer 10 to become the most distant human-made object from Earth. It continued outward through the 2000s, its distance growing by roughly 500 million kilometers each year. Scientists monitored the data for signs that the spacecraft was approaching the termination shock, watching for changes in particle energy, magnetic field fluctuations, and variations in the solar wind speed. In December of 2004, at a distance of approximately 94 astronomical units from the Sun, Voyager 1 crossed the termination shock. The evidence was unmistakable. The solar wind speed dropped dramatically, the magnetic field strength increased, and the intensity of lower energy charged particles changed abruptly. The spacecraft had entered the heliosheath, the turbulent outer layer of the Sun's domain. Voyager 2 crossed the termination shock roughly 3 years later, in August of 2007, at approximately 84 astronomical units, 10 astronomical units closer to the Sun than where Voyager 1 had crossed. The difference in distance confirmed that the heliosphere is not symmetrical. The termination shock is closer to the Sun in some directions than others, shaped by the pressure of the interstellar medium and the Sun's varying activity over the 11-year solar cycle. Inside the heliosheath, both spacecraft detected an environment that was more complex and more turbulent than models had predicted. The solar wind, now subsonic and compressed, created a thick, hot, chaotic region filled with magnetic bubbles, pressure fluctuations, and a mixture of solar and interstellar particles. The heliosheath was not a thin transition layer. It was a substantial region, hundreds of millions of kilometers deep, through which the Voyagers would need years to travel before reaching the heliopause. During this long transit, the spacecraft themselves continued to age. Their plutonium power sources decayed steadily, producing roughly 4 watts less each year. By the mid-2000s, total electrical output had dropped from the original 470 watts to around 300 watts per spacecraft. Mission controllers at the Jet Propulsion Laboratory began systematically shutting down non-essential systems and heaters to conserve power for the most scientifically valuable instruments. Each decision about which instrument to deactivate was made carefully, balancing the science, return against the risk that allowing a component to cool below its operating temperature might cause it to fail permanently. The engineering teams who had built the spacecraft in the 1970s were retiring, passing their knowledge to younger engineers who had never seen the hardware firsthand. Documentation from the original construction was retrieved from archives. Procedures for commanding 40-year-old computers across billions of kilometers were refined and preserved. The Deep Space Network continued to allocate precious antenna time to the Voyagers. Even as newer missions competed for resources, it was a quiet, patient vigil to aging spacecraft, a small team of dedicated engineers and scientists, and a whisper of radio signal crossing the solar system at the speed of light, carrying measurements from the edge of everything humanity had ever explored. And beyond the heliosheath, the heliopause waited the final boundary, the true edge of the Sun's reach, and the threshold of interstellar space. For years, scientists debated what the crossing of the heliopause would actually look like in the data. The boundary between the Sun's domain and interstellar space had never been directly measured. Those predicted certain signatures: a sharp increase in galactic cosmic rays, a corresponding drop in lower energy solar particles, and a change in the direction and strength of the magnetic field. As the spacecraft transitioned from the Sun's magnetic influence to that of the interstellar medium, but no one could be certain how abrupt or how gradual the transition would be, or whether additional unexpected features might complicate the picture. Throughout 2012, Voyager 1's instruments began registering changes that suggested the boundary was near. The flux of galactic cosmic rays, high-energy particles originating from distant sources across the Milky Way, normally partially blocked by the heliosphere, began rising steadily. At the same time, the count of lower energy particles associated with the solar wind began to drop. The two curves were converging, and scientists watched with growing anticipation. On the 25th of August 2012, at a distance of approximately 121 astronomical units from the Sun, roughly 18 billion kilometers, the data shifted decisively. The intensity of galactic cosmic rays jumped sharply and remained elevated. Solar particle counts plummeted to near zero. The plasma density around the spacecraft increased dramatically, consistent with the denser, cooler material expected in the interstellar medium. Voyager 1 had crossed the heliopause. The announcement, however, did not come immediately. The magnetic field data complicated the interpretation. Scientists had expected the magnetic field direction to change significantly at the heliopause, rotating from the orientation imposed by the Sun's magnetic field to the different orientation of the local interstellar magnetic field. But Voyager 1's magnetometer recorded only a modest change in field direction, even as every other indicator pointed to a boundary crossing. This discrepancy sparked intense debate within the scientific community. Some researchers argued that the spacecraft had entered a previously unknown transitional region rather than true interstellar space. Others proposed that the interstellar magnetic field near the heliopause might be more closely aligned with the Sun's field than models had predicted, reducing the expected directional change. The debate was eventually resolved through an indirect but elegant measurement. In April of 2013, a powerful coronal mass ejection from the Sun sent a pressure wave rippling outward through the heliosphere. When this wave reached Voyager 1's position, roughly a year later, the spacecraft's plasma wave instrument detected oscillations in the surrounding medium. The frequency of these oscillations allowed scientists to calculate the density of the plasma around the spacecraft, and the result was unambiguous. The density was approximately 40 times higher than what had been measured inside the heliosheath. It was consistent with the expected density of the interstellar medium and far too high to represent any region within the heliosphere. In September of 2013, NASA formally announced that Voyager 1 had entered interstellar space. The crossing had occurred more than a year earlier, on or around the 25th of August, 2012. Voyager 1 became the first human-made object to leave the heliosphere and enter the space between the stars. The announcement carried a weight that extended beyond the scientific details. For 35 years, Voyager 1 had been traveling outward. It had revealed the volcanoes of Io, the structure of Saturn's rings, the hidden complexity of Titan's atmosphere. It had turned its cameras back to capture the pale blue dot, and now it had crossed a threshold that no human artifact had ever reached, the boundary where the Sun's influence finally gives way to the broader galaxy. The spacecraft was still functioning. Its instruments were still measuring. Its radio signal, though faint, still reached Earth, and the space around it was no longer the Sun's. 6 years later, Voyager 2 followed on the 5th of November, 2018, at a distance of approximately 119 astronomical units from the Sun. Voyager 2 crossed the heliopause. Its crossing occurred slightly closer to the Sun than Voyager 1's, consistent with the asymmetry of the heliosphere and the different directions in which the two spacecraft were traveling. Voyager 1 was heading generally northward relative to the ecliptic plane, while Voyager 2 was heading southward, and the shape of the heliosphere differs in these two directions. Voyager 2's crossing provided something that Voyager 1's could not: direct plasma measurements. Voyager 1's plasma science instrument had stopped functioning in 1980, decades before the heliopause crossing, forcing scientists to rely on indirect methods to characterize the plasma environment. Voyager 2's plasma instrument was still operational, and it recorded the transition in extraordinary detail. The data showed a sharp, clean boundary. The solar wind plasma dropped away abruptly and was replaced by a denser, cooler interstellar plasma within a remarkably short distance. The heliopause, at least at the location and time of Voyager 2's crossing, was not a broad, gradual transition, but a relatively well-defined surface. Comparing the two crossings revealed both similarities and differences. Both spacecraft experienced the expected jump in galactic cosmic rays and the drop in solar particles. Both measured an increase in plasma density, but the magnetic field behavior differed subtly between the two locations, and the fine structure of the boundary region showed variations that hinted at a heliopause that is dynamic, rippling, and influenced by changing solar activity. The heliosphere breathes, expanding and contracting slightly with the 11-year solar cycle, and the boundary the Voyagers crossed is not a fixed wall, but a living, shifting membrane shaped by the continuous interaction between the solar wind and the interstellar medium. In interstellar space itself, the Voyagers have continued to measure an environment that is quieter than the heliosheath but far from empty. Galactic cosmic rays arrive from all directions at relatively stable intensities, no longer partially shielded by the heliosphere. The magnetic field, now dominated by the interstellar medium rather than the Sun, is relatively steady but carries subtle signatures of the large-scale magnetic structure of the local region of the Milky Way. The plasma is thin but measurable, and occasional pressure waves from solar activity still reach the spacecraft, causing detectable oscillations even at distances where the Sun itself is barely distinguishable from the surrounding stars. What interstellar space means in this context deserves careful clarification. The Voyagers have left the heliosphere, the bubble of solar wind and magnetic field that the Sun maintains around itself. They are now immersed in the interstellar medium, the gas and dust and magnetic fields that fill the space between stellar systems. But they have not left the solar system in the gravitational sense. The Sun's gravitational influence extends far beyond the heliosphere, reaching outward to the Oort cloud, a hypothetical shell of icy bodies believed to surround the solar system. At distances of perhaps 2,000 to 100,000 astronomical units, Voyager 1, at roughly 165 astronomical units from the Sun as of the mid-2020s, has barely begun to cross this gravitational domain. It will not reach the inner edge of the Oort cloud for roughly 300 years, and it will not pass through the Oort cloud entirely for perhaps 30,000 years. The Voyagers are, in this sense, still within the solar system. They have crossed the boundary of the Sun's particle influence, but remain firmly within its gravitational embrace. The distinction matters because it shapes how we understand the spacecraft's position. They are interstellar travelers in terms of the medium they are passing through, but they are still solar system objects in terms of the gravitational forces governing their trajectories. Neither spacecraft is aimed at any particular star. Voyager 1 is heading in the general direction of the constellation Ophiuchus and will pass within approximately 1.5 light years of a star in that region in roughly 40,000 years. Voyager 2 is heading toward the constellation Sagittarius and will pass near a star called Ross 248 in approximately 40,000 years as well. These are not close encounters by any meaningful standard. The spacecraft will drift silently through interstellar space for tens of thousands of years, their instruments long dead, their power sources exhausted, their golden records intact but unplayed, carried forward by inertia alone through the vast emptiness between the stars. But for now, in these final years of active operation, both Voyagers remain alive. Their instruments continue to return data. Their signals continue to reach Earth, and the measurements they are making the first direct observations of interstellar space from within it represent a kind of science that cannot be replicated by any telescope, any simulation, or any theoretical model. Only a spacecraft physically immersed in the interstellar medium can tell us what that medium actually looks like, how it behaves, and how it interacts with the fading edge of our sun's influence. Every day, both Voyagers travel roughly 1.5 million kilometers farther from home. Every day, the signals grow a little fainter, the power reserves a little lower, the instruments a little colder, and every day the data continues to arrive. Behind every measurement returned from interstellar space, behind every course correction and software upload and instrument calibration, there have always been people. The Voyager missions are often described in terms of spacecraft and trajectories and scientific discoveries, but the program has also been, from the very beginning, a profoundly human undertaking sustained not by automation alone, but by the dedication of a small and shrinking team of engineers and scientists who have kept two aging machines alive far longer than anyone originally imagined possible. When the Voyagers launched in 1977, the mission team at the Jet Propulsion Laboratory numbered in the hundreds. Engineers specializing in propulsion, telecommunications, power systems, attitude control, and scientific instruments filled entire buildings. The mission control room buzzed with activity during each planetary encounter, with scientists crowding around monitors as images arrived, sometimes gasping audibly at what they saw. The Voyager project was one of NASA's flagship programs, richly generously funded, but supported by the momentum of a space agency still operating in the long shadow of Apollo. By the 1990s, with the planetary encounters complete and the spacecraft heading into the quiet emptiness beyond the planets, the team began to contract. Funding was reduced. Engineers retired or moved to newer missions. The control room grew quieter. By the 2000s, the entire Voyager operations team at the Jet Propulsion Laboratory had been reduced to a handful of people, a small group of engineers and scientists, some of whom had been with the program for decades, maintaining contact with two spacecraft that were further from Earth than anything humanity had ever built. The challenges they faced were unlike anything encountered in conventional spacecraft operations. The computers aboard each Voyager were designed in the early 1970s, built with technology that was already aging at the time of launch. Each spacecraft carries 3 interconnected computer systems: the Computer Command Subsystem, the Flight Data Subsystem, and the Attitude and Articulation Control Subsystem, with a combined memory of roughly 68 kilobytes. For comparison, a simple modern email often exceeds that storage capacity. Programming these computers requires working in assembly language, a low-level coding method that few modern engineers are trained in. The original programmers have long since retired, and their knowledge has been passed down through careful documentation and direct mentorship to younger team members who must learn to think in the vocabulary of 1970s computing. Every command sent to the Voyagers must travel at the speed of light across billions of kilometers. As of the mid-2020s, a signal from Earth to Voyager 1 takes approximately 22.5 hours to arrive. The return signal takes another 22.5 hours. A simple command and response exchange, send an instruction, wait for confirmation, requires nearly 2 full days. There is no real-time interaction. Every command sequence must be meticulously planned, tested, and verified before transmission. Because an error cannot be corrected quickly. A wrong instruction could put the spacecraft into an unrecoverable state before the operations team even knows something has gone wrong. The power situation has become the defining constraint of the extended mission. Each Voyager's 3 radioisotope thermoelectric generators convert heat from the natural decay of plutonium-238 into electricity. But plutonium-238 has a half-life of approximately 87.7 years, meaning the heat output, and therefore the electrical power, decreases steadily and irreversibly over time. At launch, each spacecraft's generators produced roughly 470 watts. By the mid-2020s, output had fallen below 300 watts per spacecraft and continues to decline by approximately 4 watts each year. This gradual power loss has forced the mission team into a long, methodical process of triage. Instruments and heaters have been shut down one by one over the years, each decision carefully weighed against the remaining scientific value. The cameras were turned off after the pale blue dot image. In 1990, the ultraviolet spectrometer was deactivated. Heaters for various instrument platforms were switched off, allowing those components to cool to temperatures well below their designed operating ranges. In some cases, instruments continued to function even at temperatures far colder than their specifications suggested they should survive, a testament to the conservative engineering practices of the 1970s, when components were built with generous margins because the consequences of failure in deep space were absolute. As of the mid-2020s, each spacecraft operates only a small subset of its original instrument suite, the most scientifically valuable instruments for the interstellar mission: the magnetometer, the cosmic ray detector, the plasma wave subsystem, and on Voyager 2, the plasma science instrument, have been prioritized. But even these remaining instruments face eventual shutdown as power continues to decline. Current projections suggest that the last scientific instrument on each spacecraft will need to be turned off sometime around the early to mid-2030s, after which the Voyagers will fall silent permanently. There have been close calls along the way. In 2020, Voyager 2's fault protection software triggered an unexpected shutdown of its science instrument after a routine maneuver sequence consumed slightly more power than expected. The spacecraft automatically entered a safe mode, turning off non-essential systems to protect itself. The operations team, working across the vast communication delay, carefully diagnosed the problem and restored normal operations over the course of several days. In 2022, Voyager 1 began transmitting garbled telemetry data due to a malfunction in its attitude and articulation control system. The corrupted data made it temporarily impossible to determine the spacecraft's orientation or status. Engineers eventually traced the problem to a faulty chip in the system's computer and developed a workaround that routed the data processing through a different, still functional section of the computer's memory. The fix required uploading new software across 22 hours of signal travel time, testing it remotely, and verifying the results all on hardware that was nearly half a century old. These incidents underscore a remarkable truth about the Voyager program. The spacecraft have now operated continuously for nearly 5 decades, far exceeding their original design life of 5 years. Every component has been exposed to cosmic radiation, extreme cold, and the gradual degradation of materials over timescales that no laboratory test could fully simulate. That both spacecraft continue to function at all is extraordinary. That they continue to return scientifically valuable data from interstellar space is a tribute not only to the engineers who built them, but to the small, persistent team that has kept them alive through decades of creative problem-solving, patient troubleshooting, and quiet devotion. The people who maintain the Voyagers rarely make headlines. Their work is slow, methodical, and deeply technical. They do not have the visibility of astronauts or the public profile of mission directors during dramatic landings. But they are the reason the data continues to arrive. They are the reason humanity still has ears in interstellar space. And then, there is the golden record, the object aboard each spacecraft that was never intended for any scientific purpose at all. The record was assembled in 1977 under the direction of Carl Sagan, with contributions from a small team that included the writer Anne Druyan, the artist John Lomberg, and several scientists and musicians. The challenge was extraordinary. How do you represent an entire planet, an entire species, an entire civilization on a single 12-inch disc that might not be found for millions of years, if ever? The team chose to include 115 images encoded as analog signals on the records. Surface photographs of Earth, its landscapes, its people, its cities, its animals, its scientific knowledge. Greetings were recorded in 55 languages, from ancient Sumerian to modern Mandarin, each one a brief hello from one small world to the unknown. The sounds of Earth were captured: surf, wind, thunder, bird song, whale calls, laughter, footsteps, a heartbeat, and 90 minutes of music were selected from cultures and traditions spanning the globe. Bach and Beethoven, alongside Senegalese percussion, Navajo chanting, Azerbaijani folk music, and Chuck Berry. The selection process was not without difficulty. Questions of representation, cultural sensitivity, and practical limitation shaped every choice. There was no way to include everything. There was no way to fairly represent every culture, every language, every musical tradition. The team acknowledged these limitations openly and made their selections, with the understanding that the record was not a comprehensive archive but a gesture, a carefully chosen introduction, necessarily incomplete, offered in good faith. The aluminum cover of each record was electroplated with uranium-238, whose known decay rate provides a natural clock. Any civilization that finds the record and understands basic nuclear physics could measure the remaining uranium and calculate how much time has passed since the record was created. Diagrams etched into the cover illustrate the position of the Sun relative to 14 pulsars, rapidly rotating neutron stars, whose precise frequencies serve as cosmic landmarks, allowing the finder to determine where in the galaxy the record originates. Additional diagrams explain how to play the record, how to decode the images, and how to extract the audio. Whether the golden record will ever be found is almost certainly beside the point. The distances between stars are so vast, and the Voyagers are so small, that the probability of interception is vanishingly close to zero. The record was never truly intended for its hypothetical extraterrestrial audience. It was intended for us. It was a mirror held up at the moment of departure, a statement of who we were, what we valued, what we hoped for, and what we wished to say as we sent our first permanent emissaries beyond the reach of the Sun. The record endures. Long after the last instrument falls silent, long after the final watt of power is exhausted and the spacecraft go dark, the golden record will continue. The vacuum of interstellar space is extraordinarily gentle on physical objects. There is no wind, no rain, no oxidation, no erosion. The gold-plated copper disk will survive essentially unchanged for hundreds of millions of years, perhaps longer, drifting silently through the galaxy, carrying its cargo of images and sounds and music from a small blue world that once reached outward and thought to say hello. As of the mid-2020s, both Voyager spacecraft continue their outward journey. Voyager 1, the more distant of the two, has traveled beyond 165 astronomical units from the Sun, more than 24 billion kilometers from the world where it was built. Voyager 2 trails slightly behind, at roughly 138 astronomical units. Both are moving at speeds that will carry them roughly 500 million kilometers farther from home. With each passing year, neither spacecraft will ever slow down, neither will ever return. They are permanent departures, the first objects made by human hands to leave the Sun's particle influence and enter the space between the stars. The data they continue to return is irreplaceable. No other spacecraft currently operates in interstellar space. No mission capable of reaching the heliopause has been launched since. Proposals have been studied, concepts for an interstellar probe that could travel faster and carry more advanced instruments. But as of now, the Voyagers remain humanity's only direct presence beyond the heliosphere. Every measurement they transmit, every reading of magnetic field strength, or cosmic ray intensity, or plasma density, represents information that cannot be obtained any other way. Telescopes can observe the heliosphere from within. Simulations can model its behavior. But only the Voyagers can report what interstellar space actually feels like from inside it. Their instruments are aging. Their power is fading. The mission team continues to manage the slow decline with the same patient ingenuity that has sustained the program for nearly 5 decades. But the laws of physics are not negotiable. Plutonium-238 decays at a fixed rate. Each year, the generators produce a little less electricity. Each year, another decision must be made about which instrument to keep and which to release. The final scientific measurements will likely be taken sometime in the early to mid-2030s, after which there will no longer be enough power to operate any instrument at all. When that day arrives, the spacecraft will not cease to exist. They will simply go quiet. Their transmitters will fall silent. Their computers will stop processing. Their instruments will cool to the ambient temperature of interstellar space, a few degrees above absolute zero. But the physical structures, the 10-sided bus, the golden antenna dish, the instrument booms, the radioisotope generators, and the golden record bolted to the side will persist. In the near-perfect vacuum between the stars, there is almost nothing to degrade them. No atmosphere to corrode the metal, no weather to wear the surfaces, no radiation intense enough to significantly alter their structure over human timescales. The Voyagers will drift, slowly into imperceptibly. They will continue outward, each following the trajectory established decades ago by the gravitational assists of giant planets. Voyager 1 will pass through the Oort cloud over tens of thousands of years, eventually emerging on the other side into the open space of the galaxy. In roughly 40,000 years, it will pass within approximately 1.5 light years of a star called Gliese 4145 in the constellation Camelopardalis. It will not enter that star's planetary system, if one exists. It will simply drift past, a silent artifact from a distant civilization, unnoticed and undetected, unless something extraordinary intervenes. Voyager 2 will make a comparable passage near the star Ross 248 in roughly the same time frame, and then both spacecraft will continue onward. Their orbits governed by the collective gravitational field of the Milky Way, circling the galactic center, along with the hundreds of billions of other stars and objects that make up our galaxy. Their journeys, in a very real sense, will never end unless they collide with something, an event of almost impossibly low probability given the emptiness of interstellar space. They will orbit the galaxy indefinitely, outlasting the Earth, outlasting the Sun, potentially outlasting the solar system itself. It is a strange kind of immortality. The spacecraft were designed to last 5 years. They have endured for nearly 50. And in their silent, powerless future, they will endure for millions of years more, carrying a golden record of sounds and images from a civilization that may no longer exist by the time the record is old enough to show its age. The legacy of the Voyager program is not easily measured in conventional terms. The missions produced tens of thousands of scientific papers. They discovered dozens of new moons. They revealed active volcanoes, subsurface oceans, ring systems, magnetospheres, and atmospheric dynamics that rewrote textbooks across every subfield of planetary science. They defined our understanding of the outer solar system for an entire generation of researchers and inspired countless young scientists to pursue careers in astronomy, planetary science, and space exploration. In strictly scientific terms, the Voyager program is among the most productive space missions ever conducted. But the program's impact extends beyond the scientific. The Voyager missions changed something about how humanity understands its own position in the universe. Before Voyager, the outer planets were abstractions, distant points of light, studied through telescopes, their moons little more than names on a chart. After Voyager, they were places. Io was a world of erupting volcanoes. Europa was a frozen shell, hiding a possible ocean. Titan was a world with weather and chemistry. Triton was a captured wanderer, with geysers erupting from nitrogen ice. Each of these worlds had been transformed from an astronomical object into an environment, a place with geology and atmosphere and history, a place that could be studied, understood, and wondered about in the same way we wonder about landscapes on Earth. The pale blue dot photograph accomplished something similar in reverse. Instead of making distant worlds feel closer, it made Earth feel smaller, a single pixel of light in an ocean of darkness, carrying everything and everyone that had ever existed. The image did not contain new scientific data. It contained perspective, and perspective, once gained, is difficult to lose. The Golden Record, too, carries a meaning that transcends its physical content. It is not a comprehensive record of Earth. It could never be. It is a selection, a gesture, a carefully assembled introduction created by a small group of human beings who understood that the message mattered more than the likelihood of its reception. The act of choosing what to include, what music, what images, what words, what sounds was itself a statement about what humanity valued at the moment it first sent something permanent beyond the sun. The record is both a time capsule and a letter, written not to any known recipient, but to the possibility that recipients might exist somewhere, somewhen, in the vast and largely silent galaxy. There is a quiet comfort in knowing the Voyagers are still out there, even after the last instrument shuts down, even after the final signal fades below the detection threshold of the Deep Space Network. The spacecraft will continue. They will carry the golden record through interstellar space for longer than human civilization has existed. They will outlast every building, every monument, every written document currently on Earth. They are, as of now, the most enduring physical objects humanity has ever created, not because they were designed for permanence, but because the environment they entered is so empty and so gentle that even fragile things can last forever. The Voyager missions began with a rare alignment of planets and a small team of engineers who built 2 spacecraft by hand in a clean room in Pasadena. They were designed to visit Jupiter and Saturn. They visited 4 planets, dozens of moons, and crossed into interstellar space. They changed our understanding of the solar system, captured an image that changed how we see our own world, and sent a golden message into the darkness on behalf of everyone who has ever lived on this small, pale blue planet. Tonight, as you listen to this, both Voyagers are still moving. They are farther from Earth than any object has ever been. The sun behind them is just another star. The space ahead is vast and quiet, and very, very old. And somewhere on the side of each spacecraft, A golden record waits patiently, carrying the sounds of wind and whales and laughter and music, drifting outward through the silence between the stars, saying hello to no one in particular and to everyone at once.